Good evening, everyone, and welcome to today's session of Saturday Talk. We are privileged to have Dr. Narendra Dhokey as our today's speaker, and he's going to deliver a session on overview on energy materials. Please give a moment to introduce Dr. Dhokey. Dr. N.B. Dhokey has completed his MTech from IIT Bombay and PhD from VNIT Nagpur. He spent his initial 6 years in steel plant and then moved to teaching and research. He is presently, as I said, is a professor in Meteorology and Material Science Department, COEP Technological University of Pune. He is a former head of Department of Meteorology and Material Science. He teaches to BTech and MTech students subjects such as transport phenomena, meteorological thermodynamics, steel making, tribology of materials, energy materials, and powder metallurgy. And he is the approved supervisor of University of Pune for guiding PhD students. He has completed sponsored projects from ISRO, UGC, DRDO, John Deere India, DST, and BRNS. Besides, he has executed consultancy assignments from several industries. He has established state-of-the-art powder metallurgy, tribology, and cryogenic treatment material processing lab. Dr. Dhokey published several papers in international and national journals and few patents to its credit. He is honored by IIM Certificate of Excellence in the year 2011 for his distinguished services in the overall growth of IIM Pune chapter. He is a life member and vice president of PMAI IIM MRSI. He was co-convener of NMD 2014 organized at COEP and organized events for the industry relevance. So, sir, it's over to you now. We'd like to listen to you.
Yeah. While discussing on these energy materials, we always keep this concept in mind while executing some of the research projects. So, the environment, society, and economics into account. So, finally, the sustainability of any process is very, very important in today's world. Okay, so why this topic is so important? Because when you look at what world is doing with energy material, you'll find some relevance and references. Top you can say the emerging technologies of 2020. You'll find that sun power chemistry, low carbon cement, and then you have a green hydrogen. So at least when you look at this, the relevance of this topic, so it has some importance in the world, emerging technologies. So that is why, this is catching up the attentions of the learner and researchers. So if you look at even the US document, the emerging technologies, you'll find the relevance of, these energies, advanced nuclear energy technologies, and then directed energy, which is something related to laser weapon and all. And then you'll see the renewable energy generation and storage, semiconductors, and microelectronics. So these are all the topic of relevance in terms of the energy is concerned, and we find energy usage in different forms. So when you look at our government policies, today's government policies which are available in the public domain, and this is Atmanirbhar Bharat, and if you look at the content, you'll find that these are all the relevant disciplines of research, and one of them is electronic, and of course some materials of energy would definitely be in application in different segments. So here is the scope to work upon. And then the hydrogen economy, the policy document of the government is also available, where it also mentions that how do we storage, what should be the storage of the hydrogen, not in the liquid form, but if it is for the onboard application, it should be in the hydrate form. So there is a different class of alloys that comes up as hydrogen storage alloys. And then you'll also find in the past some how this chip shortage is making life difficult. So we also realize the importance of chip, which is definitely the semiconducting materials. And also in the news you'll find some relevance of the battery, how the government is supporting the energy in different ways to to make it self-reliance in particular sector. And recent past, the government has also issued the document on the semiconductor. So you'll find that a lot of relevance is given to this energy materials, which is used in different segments, influence the quality of life. Now, while doing so, it also realizes that we need to when you are developing certain material or process, we need to look at the circular economy. So this is the current linear economy: take, make, and dispose of, and this is the circular economy. So we should have the more recyclability into the system, and of course the reduced carbon footprint. That's a very important part of this energy materials or any process for that matter. Now, if you look at the energy, we use different form of energy. Say for example, this is very common to all of us. This chemical energy. We use batteries. It's a process of oxidation and reduction, and that's how we produce energy. So likewise, we use different gadgets, equipments, wherein we use we convert one form of energy to other form of energy. Like heat energy, we IC engine, we burn fuel and we produce some the motion to the system. So likewise, you'll find that we all use different forms of energy in our day-to-day life in running different systems and to make our life happy and comfortable. Now, if you look at the world energy scenario on consumptions, so this is a scale up and the very relevant document up to 2040. So you can see that here the nuclear energy growth rate would be not so would be dramatic, but the renewable segment will catch up. And of course, here is you'll find that the coal, petroleum, and other liquids, these are all carbonaceous. You can see the input material as fuel, and that is going to add to the carbon footprint. So there is, it shows that we have a lot of scope for here to replace these carbonaceous fossil fuels by some means of renewable energy. So, and for which you need to develop new materials and need to work on the research fund, and this definitely gives you a scope to work on different strategy for generating the energy. Now, the very important one is today is the hydrogen. So we talk about the green hydrogens and then gray hydrogens, and there are different forms of energy from which the hydrogen is produced. The green hydrogen typically we look at where you are trying to get the energy from the wind, and then you can have this electrolyzer through which you are splitting the water and producing hydrogen. So this is how it is defined as a green hydrogen. Now, if you say that the fossil fuel or the hydrocarbon gas also we can split it and produce hydrogen. So this is treated as a gray hydrogen. And there's another category where you precipitate out carbon and only produce hydrogen. It is called as blue hydrogen. And if you are producing a hydrogen through the nuclear energy process, it is called as pink hydrogen. So there are many definitions that are coming up in the market. So it will be interesting to look at those definitions. And this photovoltaic cell, when you are coupling this electrolyzer with the photovoltaic cells, then you are truly, producing the green hydrogen. So this is how the definition of green hydrogen has been, found in the documents. And here is, the carbon footprint in the whole process. Directly, it is not seen here. Maybe there could be some indirect, addition of carbon footprint while manufacturing. These are some of the, the devices, components for this photovoltaic or wind energy. So, but this is how the present definitions of the green hydrogen. And there are a lot of application of green hydrogen for the material processing and for running the fuel cells. So we'll see that one by one from the materials point of view. Now there is a very published document in the public domain by McKinsey. So if you look at how this at present and by 2050, the cost of green hydrogen will come down as we give more emphasis on the renewable energy. So it will come down, and the fossil fuel cost by which we produce the gray hydrogen, which will go up. So this is how it's based on some assumptions. The strategy has been proposed that we may use more green hydrogen in new applications and replacing the carbon-based economy by the hydrogen-based the processes. So as we know that for producing 1 ton of steel, it produces 1.85 tons of CO2, which is 8% of the global CO2 emissions. So this is very important, from the pollution point of view or carbon footprint point of view. So I think a lot of work we need to do it for next 10-20 years. And there are different documents which are available in the public domain, particularly in the context of the energy. Now this right hand chart, if you see here, you will see that this is up to 2050. Now the steel is produced nowadays by the blast furnace and basic oxygen process or by electric process. So this yellow part you will see, this is the scrap plus electric furnace, the processes that are used. But as we move towards 2050, you will find that more scrap recycling through the electric arc furnace will be done, and less amount of steel would be produced by the blast furnace. And blast furnace typically consume carbonaceous material like coke for the production of steel. So this is what a projection that has been seen in the published document, and there is a wonderful model has been created here. The 3 E's: economy, energy, and emissions, and they are all interconnected. How it is interconnected with technology is also shown here. So it is a very interesting document to look at and understand what will be the future in terms of energy and energy materials and the applications to make to reduce finally the carbon footprint and make a planet green. On the basis of this hydrogen, if you just look at the projections, so we are aware that the steel product steel making route emits a lot of carbon dioxide, and if you just look at this particular histogram on the CO2 reduction. This is what proposed in the Paris Agreement. By 2050, we should be this level from 2,800 to 400 to 600. The production, 1 million tons of CO2 that would be going to the environment. So these are the projections which has been put up by the Paris Agreement. Now, if you look at the global steel demand, that will go up. Okay, so naturally you need to make a very common operating window. So if you look at the overall summary, if you divide this 1 million tons of CO2 by this, how much million tons of steel that you have produced, so you get this particular graph. So it is expected that by 2050 we may be able to reduce by 90% this CO2 emission. So if you work simultaneously on the renewable energy sources, and if you could able to produce hydrogen in a very economical way using the electrolyzer and coupling with the the renewable sources, so you can make a green hydrogen, and that's what the strategy it has been proposed here. So we may able to do it by 2050. Now in the particular in this steel segment, so this is in fact the scenario here that the steel is produced by use of coal, oil, natural gas. And of course it emits a lot of CO2 into the environment. Now the middle one is this is a direct reduced iron and electric arc furnace route, wherein you can use some natural gas for the reduction of iron ore. So this is in fact we call it as improved way of making a steel, but we need to go a little more further, where you can avoid the natural gas, make use of the hydrogen, and that too through the water electrolyzer. And how this where from this water electrolyzer will get energy, it will be obtained from the solar or renewable sources. So if you could make a circuit like this, then it will be truly a green steel, and this would take some few years next to get this picture on a commercial level. So it is so you can say that there are simultaneous work is happening in all these tiers. In fact, at a laboratory scale, we could able to produce a green steel in our college laboratory, but we'll have to go a little more to scale up and make a prototype at a later stage. Now on the fuel cells, if you see that now we are very much get fascinated as when the news comes that the car is running on the fuel cells. Now if you look at here is the fuel cells, here is placed the battery, and then fuel cells, the entire system here, and then you get a hydrogen from this tank, so liquid hydrogen. But this liquid hydrogen handling is not allowed, in fact, or it is prohibited. So it is suggested that for any onboard application, we must have hydrogen in the form of hydride, and this hydride, it's a the material based. You can have say titanium iron hydride or say aluminum hydride, and on heating it will release the hydrogen, and when you are refueling it, hydrogen will get absorbed. So something this is called as the hydrides. So once we get a hydrides, then things would be quite safe to use for onboard application. For outboard, absolutely fine. You can use liquid hydrogen for running the fuel cells, but for onboard application, this is what is suggested. And because of this recent past, you'll find some the publication domain, there are different hydrogen storage alloys are coming up. Now if you look at to run a fuel cell of 55 kilowatt, this titanium hydride the metal hydride is, people have produced, and it is says that, for the weight of this metal hydride requires is about 280 kg, and in which it stores about 5 kg of hydrogen. So this how some experimentation research work is happening all across the globe, and there are different combinations of the alloys. If you look at this lanthanum, nickel, aluminum, manganese, nickel, magnesium, in fact, it has a good affinity with the hydrogen. So these are all the applications or the alloys that are available in the market to run some small fuel cell, laboratory scale fuel cell. But at the same time, people are very ambitious. In fact, in the research domain, they have marked a window here. Okay, so this is what the target to achieve this, to manufacture this, particularly the hydrogen storage alloys. Amongst all these alloys, you will find only this is commercially available: sodium boron hydride. Somewhere I had an opportunity to see this particular hydride alloy, but others are under the development, and there are a lot of challenges also there in the development of hydrogen storage alloys. And these are all the required for the onboard applications to have the vehicles safe, easy to handle, and less hazardous. So these are all the things which are behind this, and therefore this lot of work is you see in the public domain. And this the histogram provides the hydrogen storage capacity. Now, if you look at this, particularly this chart, you will see that 350 bar hydrogen, cylinder, we can store 23 kgs of the hydrogen. Now there are some, this is liquid hydrogen here. We can store 70 kg and per dual cylinder. And then there is a lot of other alloys, sodium, aluminum hydride, and nitrogen. This is ammonia, which is very commonly used in many material processing industries like powder metallurgy industries. You can crack this ammonia. In fact, for the heat treatment also, you can crack the ammonia, you can separate out, you can use the nitrogens, and nitrogen will go leave the system. So likewise, the storage capacity, depending upon the compound and the compositions, it is varying. And this is what is available commercially, a bit costly, sodium boron hydride, and it has a very high capacity. And beyond that, the aluminum hydride has still more capacity to hold the hydrogen. So this would come up as one of the the hydrogen storage the system to run such onboard system where you would like to run fuel cells. So for fuel cells running, you require a hydrogen to make it a vehicle green, and this hydrogen can be supplied by this the metal hydrides, which are rechargeable. You can dissociate the hydrides, and you can after the consumption of hydrogen, you can charge it by supplying the hydrogen, which is produced by the renewable and electrolyzer sources. So there are apparently there are three categories that are studied in the public domain. Now these are challenges I think they requires to be addressed, particularly when you are hydrogenizing the alloy. So a lot of heat is generated, 33 kilojoules, and while doing so, we need to extract this heat. So it requires a proper balancing, the cooling and heating. So here is the trick and the expertise is required here. And while doing so, the entropy of the system also goes up. So entropy of the system is the overall entropy of the charging system goes up. So need to control it. It has to be under control. So you need to design a cooling system so that you can safely charge and recharge by hydrogen. And while doing so, the real problem arises when you consider rapid filling rates. Okay, so the this is very important. That when you are charging a metal hydride, if you could charge in short time, it's always welcome. But if you are taking a half day or whole day, so that's not required, or that's not attractive proposal to the common users. So therefore, we need to work on how fast we can charge. So the 83 megajoule of heat is generated during refueling will need to be dissipated at the rate of 0.5 megawatt, which is extremely challenging engineering problem that is not likely to be solved by moderate improvement in heat exchangers. Okay, so these are all the challenges associated with the metal hydride development. And if you look at the government policy which is available in the public domain, it has a mention of the metal hydrides, and I think it was released in 2005, and it has many national labs have worked on, but a real product is yet to come. Now, beyond this, there are a lot of scope for the, extracting, harvesting the heat from the waste. Now, if you look at the whole, engineering, wherever the heat is produced, you will find that, the 34% of the energy is used for the applications, whereas the 66% of energy is lost, typically the thermal power, nuclear power, automobile, waste incinerator, factory, glass making, aluminum industries, and so on. So this is really of concern to us, and therefore, there is a way to, extract the heat out of this, or harvest the heat out of this for the energy production is using the thermoelectric material. Okay, so this is also again a topic of very priority, you can say. And for example, if I could mention here a case like in hot rolling slab. So the hot rolling slabs, when it comes out of the rolling mill, the temperature is certainly above 900 degrees Celsius, red hot. So a lot of heat energy which gets radiated and it lost into the environment. So what it can be done, you can have an arc here, and all those semiconductor modules can be fitted in this manner. So you can, receive this heat from this source, and then you can convert this into electricity. So this is what is the model wherein you can have the P-type semiconductor, N-type semiconductor, and definitely you can make use of this concept of Seebeck effect in converting the waste heat into the electricity. So this is called as thermoelectric, generator. Now, in the research domain, you will also find people are using different softwares, before just to cut down their, development time. And these softwares are available. It takes into account different, physics, material science into account, and that's how this CalPAT software is being used by one of the researchers to design the alloys, to design the thermoelectric generator or semiconductor alloys through this, CalPAT simulation software. And it's available as a brand name, ThermoCal software. So they say this particular software. So on the front batteries, which is also very catching attention. Now, if you look at this lithium battery, so here lithium metal oxide here, and you will see this is a cathode. On the other side, you will see the anode, where lithium plus carbon graphite is mixed together to make the anode. So the whole assembly, you find that the requires the combination of metal and oxide, and where the anode and cathode decides the the success of this battery. So there is another option available, the iron. Iron is also can be used as a battery material, and at least commercially not available. People are researching on this front. This iron can be one day it will come out as iron battery to replace lithium. And here is another option the research community has given, or in fact it is well investigated, that how this battery can be charged using the solar. So it's possible. So you have to connect renewable with this battery to make it to save energy and make it green, reduce the carbon footprint while charging such batteries. And this is the graphene based batteries. People are are trying to develop, and there are some examples in the public domain. I don't know the commercial applications, but these are all the concepts which are well proven at the laboratory scale. Only the scale up that would decide the success, in market. So we just to add little more on this, we also did some work on the soft magnetic materials. It got published in American journals on evaluation of magnetic properties of ceramic coated soft magnetic composite and its simulation for microwave devices. Now, this is the setup that we designed, and we also filed a patent on this. So here we coat iron powders of say 100 micron by ceramic like MgO, and this is the XRD graph, and these are all the properties which are usually studied for these microwave devices. And this is a small piece of work which we published recent past. On the microwaves, normally we talk in terms of the wavelength 1 mm to 1 meter and frequency 0.3 to 300 gigahertz, and they require the consists of magnetic and electric fields. Microwave frequencies are used for satellite communications, radar, and military applications. Now here is the different components of used here, like circulator, isolator, and there are so many phase shifters, electromagnetic interference. In all material, you'll find some use of permanent magnet or ferrites for converting or making it efficient for such applications. Because finally we require this communication system where you can receive the maximum signals, good quality signals. So you need to have a material which will convert the signal into the useful part of it for communication purpose. So this is again the area where you require materials with the relevant rare earth materials for the development of this. And on small front, the metals can also be used for the energy applications. Now, if you look at the whole scenario of coal-based thermal power stations, almost occupies 50% of the energy that we consume, and the rest is comes from the gas, diesels, hydro, wind, and nuclear, and very little amount of nuclear energy. On application-wise, consumption-wise, you'll see the 40% of energy consumed by these industries, and rest is the bifurcation here. And why we so concerned about that? This is the recent, it has published it has come in the newspaper that how this the carbon emissions or the pollution that caused by the thermal power plant, affects the ecology and the human health. So this was a good survey. It has come in. It had been the particular Times News. So that is why I have listed here. So considering this aspect into account, that how do we reduce the coal consumption? How do we generate energy? So as a curiosity, at our level, we started with a small project for the BTech, and if you could look at the enthalpy of these reactions. Now this carbon is coal. You'll see that how much you produce, minus 393 kilojoule per mole. And if you burn iron powder, how much you produce, minus 412. So almost same, or you can say slightly more. And if you use hydrogen as a fuel, you produce minus 285 enthalpy of the reaction. So it means that the exothermicity is more involved with the iron oxidation. So we thought of, why not burn iron powder? So we also saw some published literature that which metal could give the energy density. Energy density, this is kilowatt hour per liter volume wise, and this is specific energy density kilowatt per kg. So you'll find that our traditional materials like coal is here, gasoline is here, diesel is here, biomass is here, hydrogen is here, and here is iron. So on this front, you'll find the energy density is very good, and the specific energy, although it's less, but it's manageable because it's a very close proximity. And of course, even if the energy density is less, but there is no pollution deterioration. So that way, I think we can look at such a element as energy materials. Aluminum could be one of the energy materials. Silicon could be one of the energy materials. So whatever the exothermicity or whatever the exothermic reaction that it produce, that energy can be very well utilized for this purpose. So this is what a schematic diagram I'm showing it here. Where we fabricated a burner, and this is what the flame. This is actual photograph of the burner. So here we need to do it more on this designing of the burner for further successful prototype. So aluminum is also studied by someone can also act as a good energy materials, and of course it is used for rocket and so many applications. In fact, in firecracker also use aluminum. But why not for our own consumptions aluminum to replace the carbon and use the waste of the aluminum as aluminum oxide back to the Herolard process to aluminum. So the particle size also has impact. The smaller the particle size, you can ignite at a very low temperature. The temperature of the ignition would be less if the particle size is less. So likewise, the surface area of the particle also makes some sense in the rate of ignitions. Okay. Now on the front, the rare earth elements for the electronic devices, you will see that so many applications of rare earth metals are used: electronics, catalysts, and magnets, metal alloys, ceramics, glasses. So full of the gadgets that we use in our day-to-day life, you'll find a lot of application of the rare earth metals for the smoothing of the our own life. Yeah.
A flow battery with ion system, will it be efficient enough and cheaper than hydrogen economy?
Right now, see, the iron powder is very much, available in abundance, So it has been used in powder metallurgy segment. So you can very well start with the iron powder. In fact, the cheapest kind of iron powder could be from the mill scale. So the cost is further come down, and the mill scale iron powder is used. It has a very high surface area, lot of porosity because of it is virtually a sponge iron, and this iron powder can work very well as reactive. Whereas the hydrogen would not be affordable at this point of time, because we are presently producing hydrogen from the fossil fuel. But if you could develop electrolyzer, in fact L&T has set up a commercial electrolyzer. That is what I saw in newspaper, that they are producing the hydrogen from the electrolyzer. I don't know whether they have coupled that electrolyzer with the renewable energy like solar or wind. So then it would be truly a green hydrogen that will be of relevance to us, and the cost may further come down, because cost is the main barrier. But sometimes also people should think that when the cost is initially high, but you have if you are using hydrogen for some application like iron ore reduction, you may see cost little high, but you don't have carbon footprint. So somewhere in the latter stage you may compensate the cost, and the slag wise also, the slag volume will also come down in the real steel making process. So I think in all angle, I think we should think and make a justification. That is what I feel. Thank you very much.